Good afternoon, everyone. Okay, so far what we have done, we started with the distributions of continuous random variables. We finished normal distribution our last lecture. Now today we are going to start two more distribution about the continuous random variable. The first one is the log normal distribution. So first we will define this log normal distribution, and then I will show you what are the PDF and CDF of this distribution. The log normal distribution is the distribution of a random variable whose logarithm follows the normal distribution. So log normal distribution is basically a distribution of a random variable whose log follows the normal distribution. Now, as you know, the normal distribution, it was defined as the normal distribution was defined where the x greater than equals to minus infinity to less than equals to plus infinity. So this was the range of our normal distribution that we studied last time. Now in log normal distribution, we have x is defined as a positive because we are talking about the log, and this range is the same. Now if y is equals to y naught times y1 times y2, and we take this product up to n values of y. Now I am going to the natural log on both sides, so this will become natural log of y. It is equals to natural log of y naught times y1 times y2 and up to y of n. Now as according to the log property, these are being multiplied, so I can add them and apply the natural log to each and every term. So this term on the right hand side will become natural log of y naught plus natural log of y1 plus up to so on. The n term will be plus natural log of y of n. That will be our last term, and the left hand side is natural log of y. Folks, I need to go to the next slide, please. If I put, for example, x is equals to natural log of y and my x is, now the previous term will be x is equals to x naught plus x1 plus x2 plus up to so on. The last term will be x of n. Now for n large values, our x will follow normal distribution. Then y that we define here is set to follow log normal distribution. So that means this y is the log of n, and the log normal distribution, just like the normal distribution, is defined using mu and your sigma values of x. Now this is the PDF that we discussed last time for normal distribution. Log of f of x is equals to 1 over 2 pi sigma of x exponential of minus 1 over 2 sigma x square x minus mu of x whole square. Now this was the PDF that we defined in our normal distribution term. Now because we are using this variable here, so what I will say that as x is equals to log of natural log of y, so the derivative of this term will be d of x over d of y, and that will be equals to 1 over y. So this is what we need to place here. I need to go on the next slide, please. Now, according to the variable transformation, f of y will be is equal to f of x into d of x over dy. Now this term I just figured out that is equals to my 1 by y. And this is my PDF. So it will be 1 over 2 pi square root sigma x exp of minus 1 over 2 sigma x square into x minus mu of x whole square times 1 over y. Now suppose that your mu of x is equals to natural log of y naught, and your sigma of x, the standard deviation, we are denoting it with the W sign. So this implies that if I have x minus mu of x, that will be equals to natural log of y minus natural log of y naught. Or I can say that this will be x minus mu of x. Now this is the log property again. We have two log terms are being subtracted. So we take natural log and we use the division here. Y over y naught. Now y naught here is the median value of y, or the best estimate of y. Now I'm going to take property and I will put that into my this equation on the next slide. I'm going to the next slide, please. So my f of y will become 1 over 2 pi this will be my w of y times exp minus 1 over 2 w square into natural log of y over y naught, and we take the square of this term and close the parenthesis. So this is your PDF for log normal distribution. Now in order to obtain CDF, of log normal distribution, we will use F in caps or the uppercase for the CDF is equals to phi of z, and this will be 1 over w natural log of the ratio of y and y naught. Okay, now this thing is the same as we were discussing in our last term, that is the standard normal distribution. And how we obtain this? From the tables. Now this is what we get from the tables. What does it mean basically? In the log normal distribution, this is the term that you need to calculate, and then we find out our phi value from the tables. Now because of x is equals to natural log of y, our f in terms of x and x will be equals to f of y and y. Or I can say that this term will be equals to phi of z in terms of normal distribution. If you remember, this was phi of z of x minus mu of x over sigma of x. Or I write it down as phi of z into 1 minus sigma x of x minus mu of x. Now, if you recall from our previous slide, let me go back here. This term x minus mu of x is defined as log of ratio of y and y naught. So here I'm going to replace this in the next slide, please. So my f of y at y will be phi of z into 1 over w natural log of y over y naught. Now here we define it. If our y belongs to the log natural distribution, we have mu of y as y naught exp of w square over 2, and the standard deviation variance is equals to y naught square exp of w square, and we multiply it with the exp of w square minus 1. Or in other words, I can say my w, which is the standard deviation here, is the square root of natural log of sigma y square over mu y and the square of mu plus 1. This goes to all actually. And my y naught will be equals to mu of y over exponential of w square over 2. Now, depending upon the value of the w, the shape of the log normal distribution will change. Oops, I need to go on the next slide, please. So let's draw the graph that we do in every distribution here. Now this is my graph in terms of log normal distribution. It will be between your capital Y and f of y. Now if you have the higher value of the w, the shape of the log normal distribution will be something like this. I'm just trying to make it as closer to the textbook as I can. So this is at the value of w square of 2.25. Now if you have a lower value than this, the shape will be something like this. On this one I am drawing on the w square value. Now, in case you have a value lower than 1, the shape will be something like this. And this line is drawn at the value of 0.25. Now, one thing you can notice here, if I have the smaller value of W square, our shape is more closer to the normal distribution. So I can say that for smaller values of W, the log normal distribution will tend to the normal distribution. Folks, I need to go on the next slide, please. Now, in terms of the normal distribution, if you recall, the graph that we draw was something like this. And one of the important property of the normal distribution was it was a symmetrical graph. It was a symmetrical graph with mean, mode, and median were equal. But this is not the case in the log normal distribution. That's because the graph is not symmetrical in the log normal distribution. So I'm going to draw one more graph here. Now this is the graph for log normal distribution, where I have my mean lying here somewhere. The median is lying here. And my mode is lying here. This point is what is my mode. This is the log normal distribution. And why we don't have mean mode equal? That's because it is not symmetrical. Now, to recall, I think in our third or fourth lecture, I discussed this kind of the curve has the positive skewness. The SK value was greater than 1 as the tail is going towards positive direction. Folks, I need to go on the next slide, please. Now we will do one example here. The breaking strength R of a cable can be assumed to be log normal distribution with a mean value of 80 kip. This is the unit for the force indicating kilopound, and standard deviation of 20 kip. KIP is the unit of your force, is the kilopound. Now the first objective is, if our load P of magnitude (60 KIP) is hung from the cable, calculate the probability of the cable. This is our first objective. The second objective here is the magnitude of P cannot be determined with certainty suppose it could be either 40 KIP or 60 KIP. Having the probabilities of if it is 40, the probability you get is the 0.3, and if it is 60, you get the probability of 0.7. Okay. Now he's going to calculate the probability of failure of the cable. So the breaking strength R of can be assumed to be log normal distribution with the mu value of 80 and standard deviation of 20. The first objective is, if a load P of magnitude 60 kPa is hung from the cable, calculate the probability of failure of the cable. Now, I need to go on the next slide, please. So what is our solution for this? So we know that this R variable follows the log normal distribution, and the two parameters are mean and the standard deviation. Now you know that the mean is 80, standard deviation. These are the parameters here. Now we will use our equation that we just derived for R. Will be equals to phi of z into 1 over w natural log of y over y naught. Now, because we are talking about here, this y is basically will be p. So I can say this will be 1 over w natural log of y over y naught. Now what we need to do, we need to calculate these parameters. Our first is the w calculations. So for you know that it is the log natural of sigma square over mu square plus 1, and we take the square root of this. Now once you plug in the values, your w will turn 0.246. You have your mean value, you have your standard deviation. You just need to plug in the values and you will find your w value here. Now for y naught, we have the mu over exponential of w square over 2, and you get 77.61 once you plug in your value. Folks, I need to go on the next slide, please. So just keep in mind, these are the two parameters that we have. Find out. So in the first objective, he was asking us to find the probability of rupture given that the P. Now the load here he's saying is the 60. So f of r at 60 is what we need to find. Now this will become 1 over w, which is 0.246 natural log of your r value, which is 60 here, and this is the y naught value. This will turns out to be y of z minus 1.046. Now this is the same procedure as we were doing before. We will go to our standard normal distribution tables, and corresponding to this value of our z value, know what are our probabilities. Now from the tables, I had two values. One was at minus 1.246, which was 0.1492. This is not the magic number, it is coming from our tables. And second value, which was quite closer to this, was 1.05. It was 0.1469. And again, because you have two values, you can just take the average of them. So my phi of z is equals to 0.1492 plus 0.469 divided by 2, because I am interested to take the average here, and that is my answer, 0.1481. This is my answer for part 1. Now in the part, folks, I need to go to the next slide, please. Now in the part B, he was asking the magnitude of the P cannot be determined with certainty. Suppose it could be either 40 or 60, and we have the probabilities. He was asking to calculate the probability of the failure of the cable. So the failure of the cable means basically we need to find out our probability of the rupture. So for the part B, we need to find out our probability of R. Now this, we have done a similar numerical previously. So P of R is equals to, now we have two probabilities at 40 and 60. So we have probability at 40 times probability of R given at 40 plus probability at 60 and probability of R given at 60. This is what we just find out in part 1 actually. So this at 40 it is given to you, which is 0.3. However, this probability we need to find out. Now we apply the same rules as we were doing before. We have the phi of z into 1 over w value. It remains same throughout the both parts times natural log of. Now we're interested to find at 40 over your y naught value, which was 77.1 plus this is given to you probability at 60, which is 0.7 times this probability we just find out in part 1, which is 0.1481. So the only part that you need to solve is this one. I'm going to write down the answer that you will get from the tables. 0.3 times 0.2036 plus 0.7 times 0.1481. Now again, this is not the magic number, it is coming from the tables of standard normal distribution. I shared those tables on D2L with you. Those are from those were I took from the end of your textbook. Now once you solve this, you will get your P of R as 0.1048, and that's what we are interested in. It is 0.1048. That's your probability value. Folks, I need to go on the next slide, please. The second distribution that we need to study today is the Weibull distribution. Weibull distribution. Now the PDF of this distribution is defined as f of x is equals to m over theta x over theta power m minus 1 times exponential of minus x over theta power m. This is the PDF of our Weibull distribution. Now, in this distribution, we have two parameters that you need to find out. First is the theta here. This is what we call as the scale parameter. The second parameter is your m. M is what we call as the shape parameter. This defines the shape of your Weibull distribution. So these are the two parameters that we need to have for this distribution. The CDF of this distribution is the f of x, which is equals to 1 minus exp minus x over theta power m. This is your CDF of Weibull distribution. Folks, I need to go on the next slide, please, because I need to draw the graph. The shape of this curve is something like this. This is our graph. It is starting from theta 1, which is a scale parameter for Weibull distribution. This is my 2 theta. This is my theta. Okay. And here my graph is between f of x. Now, if you have the m value, m is, as I said, it is the shape parameter. If you have m value equals to 1, your graph will be something like this. This is at m is equals to. Now, if you have m is equal to 2, the graph will be something like this. This is drawn at m is equals to 2. If you have m value higher, then this graph will be like this. This is my m is equals to 4. Now, as you can see, if I'm increasing my shape parameter value, this is 4. If I'm increasing my shape parameter value, my Weibull distribution is approaching to the normal distribution. So I can say that for, let's do it here, for large m shape m values, the shape approaches to normal distribution. Or I can say that for large values of the m, your Weibull distribution converts into normal distribution. Folks, I need to go on the next slide, please. Now, how do we define the mean and variance or the standard deviation in this kind of distribution? Mean in this distribution, mean of x, will be equals to theta. Now, this is a function which is called as the gamma. I will come back to this once I write down the formulas. 1 plus 1 over m. Just keep in mind this is half. The sigma of x will be equals to theta square. Gamma function of 1 plus 2 over m minus gamma function of 1 plus 1 over m square. Now this is a new thing for you, maybe. It's called as the gamma function. Gamma function. Now it is used for extension of the factorial function to complex numbers. Gamma function is used for extension of the factorial function to complex numbers. Gamma of x is equals to, we take u power x minus 1 and time exponential of minus u into du from 0 to infinity. Now once you solve this, the simplest formula turns out to be gamma of x is equals to x minus 1 times gamma of x minus 1. Folks, I need to go on the next slide, please. Now for integer values of x, this is defined as x minus 1 factorial. By that I mean to say, for example, if you need to take the gamma function of 3, it will become 3 minus 1 factorial. That will be equal to 2 factorial, and 2 factorial is 2 times 1, which is, and if you recall, in the factorial we simply multiplied with the number starting from that number, 3, 2 times 1. Whereas in the gamma function we subtract 1 from this. Okay, we will do one example here. The time to failure in terms of hours of a bearing in a mechanical shaft is satisfactorily modeled as Weibull random variable with m value of 1 by 2, and your theta value is 5000 hours. The first objective is determine the mean time until failure. This is our objective. The second is determine the probability that of bearing loss at least 6,000 hours. So the question is related to the Weibull distribution. Now the first is we need to find out our mean. I will go to the next slide, please. So the first objective is the mu of x is equals to theta, your gamma function of 1 plus 1 over m. Now these values are given to you, 5,000 of gamma function of 1 plus 1 over, now the m value is 1 by 2 from the question statement. This will be 5,000 gamma function of 1 plus 2, and then you have 5,000 gamma function of 3, times gamma of 3 is the 2 factorial because x minus 1, and the answer turns out to be 10,000. That's your answer for the first part, where he was asking to find the mean. Now in the second part, he was determining the probability that our bearing lasts at least 6,000 hours. So by that, I mean to say we need to find the probability when x is greater than 6,000. Folks, I will go on the next slide, please. Now this probability of greater than 6,000 is equals to, we can find it out to 1 minus f value at 6,000. This is the CDF here, and for the CDF we know that it will be 1 minus exponential of your value here, which is 6,000, divided by 5,000. This is the formula I just write down in previous slides. Power 1 by 2. Now this will be 1 minus 1. Now this is the negative sign here. It will change to the positive. Positive of exponential of minus. Now once you solve this, you will get 1.2. Power 1 by 2. Now these plus 1 minus 1 cancel out, and we have exponential of negative of 1.2 power 1 by 2. Now once you solve this, you will get 0.334. Now what does it mean? Basically, only 3.4% of all bearings lost at least 6,000 hours. So that's your answer here. I need to go on the next slide, please. Now for your practice, on the page 105 of your textbook, which is available on D12, you need to solve problems 109 to 115. Now, once you are reading the book, you will find some kind of different notations. Every textbook has their own notations. I will come back to that. But before, I will just write down how you can solve this in the Excel. So the formula for Weibull distribution in Excel is WEI. This is the formula that you need to type in. .TIST. Now the first thing, it will ask you the value of your X. The second parameter, it will ask you the value alpha. The third parameter, it will ask you the value of your beta. The last parameter is either it is true or false. If you want to have the CDF, you get your true. If you want to have the PDF, you choose your false. PDF. Now let's come to alpha and beta. This alpha, Microsoft Excel recognizes it as the shape parameter. Shape parameter, which we were saying as M in our lecture. This Microsoft Excel recognizes it as the scale parameter. Scale parameter. Now we were using it as a theta. If you mess up your shape parameter and scale parameter, you will get an error. Most likely you will get num. This is the error you will get if you mixed up your shape parameter and the scale parameter. Now, once you will read your textbook, this shape parameter is denoted as a beta book, and the scale parameter is denoted as a delta. There is no difference in the formula, it's just the notation. How if you will take like maybe books, you will have totally different notations. So the only thing you must understand, there is no difference in the formula, it's just the notation. Now if you are interested to find out the gamma function in Excel, it is EXP gamma, GAMMA ln. This is the natural log of your variable X. This is the formula for gamma. So again, when you're solving these problems, try to work both the calculations, the PDFs and CDFs that we calculated here, and Microsoft Excel. Folks, I will stop it here. If you have any question, I will be more than happy to answer. Okay, Hadis has a question. How about 1 over y at the end of f of y? What happened to that? I think you meant to say in the log distribution, Hadis, right? This parameter was cancelled out actually. Folks, is there any more question for me for today? Okay, Long is saying, could you please solve the problem 456 in the textbook? You need to email me, then I will help you out in that. We have a very limited time in the lecture, unfortunately, so you need to email me and I can help you with that. Folks, if you have any problems with your problems, just drop me an email and I will be happy to look on your solutions. Just by the way, there are solutions at the end of your textbook. I did not delete that solution before providing you the book just because of this reason, so that you can see either you are solving it right or wrong. So there is a solution of the problem at the end of the textbook. Folks, is there any more question for me today? Okay, we have a question here. Don is asking, can you demonstrate gamma function in Excel? Okay, sure. Let's do the gamma function. Now, the gamma function I mentioned you is the exp gamma ln of x, right? Okay, is this clear to everyone? Okay, thank you. So the gamma function, because it is a formula and I want to use it in Excel, the formula starts with the equal sign in Excel. So it will be exp. This is my exp here. And now I need to type in the gamma here according to the function GAM. So we have it here. Gamma log of, let's say I take it for 3. And then you close the parentheses and hit enter. Use the other one. Okay. So this is the exp. Gamma ln, yes, it's here, of 3. Okay. This is the gamma. So just keep in mind, not with log, but the gamma ln function as such. This is the function here, if you can see. Okay, let's do one more example. So if I want to take for number 4, let's say, so it will be exp gamma, and here it is gamma ln. Okay, of, let's say I take number 4. So for 4, you know, it will be 3 factorial, which is 3 times 2 times 1, which is gives you the 6. That's what the number is. Is it done with you? Folks, just give a try to these numerical in with the textbook. I mean the calculations that we are doing for the PDF and the Excel as well. Is there any more question for me, folks? You have your second assignment available on D12, and you need to submit October 15. Folks, if you don't have any more question, I can let you go. Okay, thank you very much, and see you on Thursday then.